Ahora, después de todos estos avisos, vamos a partir la sesión. Yo voy a dejar con ustedes a nuestro moderador de este momento, nuestro colega y amigo Leandro Guimaraes. Él es director adjunto de la Escuela Superior de Redes de RNP, la red de Brasil, para que nos acompañe.
Buenas tardes. Yo voy ahora a presentar el keynote por la parte de la tarde. Bruce Howe es presidente de la fuerza, tarea internacional conocida como SMART, Cable Initiative, Science Monitoring and Reliable Telecommunication, o Monitoreo de la Ciencia y Telecomunicaciones Confiables, para incorporar sensores en los sistemas comerciales de cable de telecomunicaciones submarinos transoceânicas, habilitando a Internet como conocemos para el clima, la climatización oceánica y monitoreo del nivel del mar y alerta de tsunamis y terremotos. En la estación Aloha, a 100 kilómetros al norte de Oahu, Bruce y su equipo instalaron y operaron el observatorio de cableado Aloha en el nodo de Internet más profundo del planeta, 4.728 metros de profundidad de agua. Anteriormente, después de obtener los títulos de Ingeniería y Oceanografía en la Universidad de Stanford y en la Universidad de California en San Diego, respectivamente, trabajó en el Laboratorio de Física Aplicada en la Universidad de Washington y durante los últimos 11 años en la Universidad de Hawaii, en el Departamento de Ingeniería Oceánica y de Recursos. Les pido un gran aloha para el profesor Bruce.
Thank you for the kind introduction. I believe there is translation. I apologize, my Spanish is nil. So, yes, thank you for the opportunity to come here and tell you about the Smart Cable Initiative, putting sensors into submarine cables to form a global observing array. I'm here, well, I work at the University of Hawaii, but I'm here representing this joint task force, and I'll say some more words about that. I'll begin first, though, with some motivational slides on climate and disasters to set the stage for why we need improved global observing, and then move on to these other topics. So first, we've known about the effect of carbon dioxide warming the Earth since at least 1896 when this paper was published. And more recently, the plot, oops, let's see, I need to get used to this here. The plot in the top right shows the last 1,000,000 years of temperature and carbon dioxide. And basically, the little spike at the end there is our current situation of we have twice as much carbon dioxide as normal for the last 1,000,000 years, and temperature is starting to increase. And the cartoon down there in the middle, our goose is cooked, overcooked basically. We've done this to ourselves, putting our civilization and species into this less than desirable situation. If you remember one thing from this talk, remember this slide. This shows the temperature increase on the left versus the amount of carbon dioxide emitted since the Industrial Revolution. And since the Industrial Revolution, we have emitted about 2,100 gigatons of carbon dioxide. And that has produced roughly a 1.3 degrees Celsius increase in temperature. If we burn another 700 gigatons of carbon dioxide, we'll get to about 2 degrees Celsius. And it's just a budget. So, and that'll take about 15 years at the present rate of 50 gigatons per year. So we get to choose how we want to do this. Do we want to use all of that budget and stop in 15 years. I don't think we're going to stop in 15 years. So we need to make these decisions on how to reduce the amount of carbon dioxide we're emitting in order to limit temperature. This is a short video with some
20 to 30 years ago, the sea ice covering the Arctic Ocean was dominated by ice that was many years old. This core of old ice survived all year round. Around this core, a smaller fringe of seasonal ice froze each winter and thawed each summer. Old ice eventually drifted out of the Arctic through the Fram Strait. New batches of old ice were built in the Beaufort Gyre. The gyre was a nursery where young ice grew thicker and stronger as it drifted around for many years. Today, summers in the southern branch of the Beaufort Gyre are often too warm for ice to survive. As a result, the amount of thick, old ice in the Arctic has declined significantly. In its place is young, thin ice that's likely to melt in the summer. The small amount of old, thick ice makes the Arctic vulnerable to extreme ice retreat in very warm summers. It's a situation that keeps Arctic wildlife, and the people who live there, poised on the edge of dramatic and possibly irreversible change.
So note there, the winter ice is very thin now and much less extent. That's the main point. Big changes. This is just another example on the top right showing how very small effects can add up to large effects. So when snow melts, it changes its reflectance, how much light. Well, this is Antarctica, an ice river on Antarctica. Let me back up here. Let's see. Hang on. There. Okay. The top right shows these small effects. As snow melts, it absorbs more heat and generates liquid water, generating or absorbing more heat still. And then algae starts growing. It gets dark, and basically you start forming pools of water on the ice, which then form these lakes of water on the ice, which cut down into the ice and melt it even faster. And that other was a video of Antarctica ice rivers, both going through the ice and then over a cliff. Those have been known for a long time, but the spatial extent is now much broader than it used to be. And so all of these effects combine to break up the ice more quickly than previously expected. And in fact, the two largest unknowns in predicting climate are cloud physics. This has been known for a long time. How much do clouds reflect sunlight and absorb heat and so on? And the second now that's appreciated is how ice sheet dynamics change. And what's being found is that warm ocean water, now ocean water is warmer, is coming down under the ice off Antarctica and melting the ice from below and intruding into the space between the ice and the land in Antarctica and melting the ice even faster than otherwise. The curves on the right show increase in sea level estimated just from melting Antarctic ice. Top right going out 500 years showing 15-meter increase, and then the lower right just 100 years is 1 meter. But you can play with statistics. If you look at the 1 in 20 chance, there's a 1 in 20 chance that by the end of the century we'll have 2-meter sea level rise. So do you plan for that, or not? It's up to us. So this ice is melting and the ocean is warming. As the ocean warms, in the lower left shows the deep ocean warming. The top left shows sea level rise measured by satellite altimetry. And the sea level rise is due to two factors. The expanding water, as the water warms up, it expands. And then second, as ice melts from land, it fills up the ocean with added mass. So there are these two effects, both contributing to sea level rise. And as sea level rise is not uniform around the world, and it'll be changing over time also as that water spreads out and distributes itself throughout the ocean and mixes with the other water. But there are island nations already disappearing, and this shows the Secretary General of the UN standing in water off Tavula to highlight the sea level rise. And one can simply coexist with the sea level rise, or in the lower right are new gates in the Rotterdam harbor to protect that harbor against sea level rise. So these are just two other examples, slightly more local in South America, of coastline erosion as sea level rises. Coastlines where most of the people in the world live now will recede. And don't forget, 1 meter of sea level rise, typically with 1 degree slopes, means you're taking away several hundred meters of land. So it's a large area basically. And it's affecting infrastructure, built infrastructure, and for instance, the freshwater aquifer is being affected as sea level rises. And then also as we know, there's coral bleaching going on and affecting the ocean ecosystem in drastic ways. Then just another non-ocean example. These are maps showing South America, the vegetation. So on the left, top left, is 1860, what South America looked like back 150 years ago. And then just 15 years ago. And then there are 4 scenarios there of different climate scenarios, and showing business as usual in the lower right, and then mitigation steps in between, and so on. The main point is that we do have control to some extent over what we're going to get in the future, and we need to exert some of that control. Lastly, in the area of disasters, tsunamis are significant and major disasters that occur irregardless of climate change, obviously. And here I've just highlighted some that have occurred in the South American region. In the map is shown in red are the earthquakes, historical earthquakes over the last 100 years since measurements began, larger ones. And then there's some yellow triangles there. Those are what are called dart buoys. They measure the tsunami wave height in the middle of out in the deep water of the ocean. As of a few weeks ago, there were, out of 59 buoys, 22 were not working. And here in Latin America and Caribbean, 9 out of 17 were not working. So these are expensive and unreliable tsunami sensors. Just 2 examples in Chile. In 1960, the largest earthquake ever recorded, 9.5, took place in Chile, and this plot here shows signals of up to about 4 meters in Japan. So these are big events. There's obviously the 2004 Boxing Day Sumatra event, which killed 250,000 people. And then more recently in Chile, 2010, another one killing about 500 people. So these go on all the time, and we need better early warning systems for these. So that brings us, hopefully that provides some motivation for why we need better ocean and earth observing systems. And what we're suggesting here is that smart cables can play a role in improving climate, ocean, sea level, earthquake, and tsunami information on a global basis. The basic idea is that we want to ride piggyback with telecom. So we want to share the infrastructure of submarine cables with the telecom industry. The basic concept is that telecom remains a primary mission of these cables, and so the location is primarily chosen by telecom. But we would add sensors to the repeaters on these cables. Every 50 to 150 kilometers, there's a repeater body. There's a little one shown in this inset here. It's about this big around, and there's optical amplifiers in there to amplify the optical signals in the fibers, and there's a little power, electrical power. And so we would add the very simplest sensors, ocean bottom temperature, pressure, and seismic acceleration. And slowly, as cable systems, new cable systems go in, replacing old systems, we would slowly build up a global spanning array over 10 to 25 years. And this cartoon here shows schematically one way that instruments could be added to these repeaters. So that's the basic concept slide. As I said, I represent this joint task force that was set up almost 9 years ago now to promote this concept. We are sponsored by 3 United Nations organizations: the International Telecommunications Union, the World Meteorological Organization, and the UNESCO Intergovernmental Oceanographic Commission. So we're reasonably well positioned within the hierarchy of UN organizations. And our main task is to promote this concept, facilitate. We're not actually doing things, but we're trying to connect people like here to the initiative to help move it forward. So with this capability or opportunity, we think that we can better observe the ocean. The ocean is the flywheel of climate and also the source of hazards. With more sensors, we can build up this global network of sensors for ocean observing, and hopefully for less money by harnessing the third-party investment, the submarine telecommunications industry investment in the submarine cables. So in my opinion, climate change is really humanity's greatest existential threat that we've imposed upon ourselves. And adding sensors to these cables is just one of many ways to help make measurements that then can be used to better plan and mitigate the situation. We'll be able to better observe climate change, ocean temperature, circulation, with direct impact on society, sea level rise, and disaster warning. We'll be addressing Sustainable Development Goal number 13, climate, and number 14, ocean, as well as the Sendai and Paris agreements. This is just a cartoon of showing some of the tools we use in ocean observing. Very important are satellites. There are these incredibly precise satellites that can measure sea surface height to a millimeter or so. And they keep track of the sea surface elevation over time and space. And then there's also gravity measurements that can be interpreted as ocean bottom pressure, basically the mass of ocean water. Now there are pros and cons to these, and the bottom line though is we still need the in situ measurements to provide ground truth and much more detail. There are other methods being used. Argo floats, roughly 4,000 of these float around the ocean at any one time. making temperature and salinity measurements. And then also these dart buoys, again, I mentioned for observing tsunamis. Basically a bottom pressure sensor, acoustic telemetry to a surface buoy, and then satellite comms back. These, though, unfortunately, suffer from, well, first of all, high latency, like 15-minute latency overall, and then also in the tropical areas, often vandalism, and then simply bad weather destroys anything at the air-sea interface. So the buoys get destroyed during the wintertime, for instance. But there are many different ways, and we will be adding this component of cabled instruments along the ocean floors. This just shows some simulations of in this case, a scenario of cables, and this would be pressure and temperature along one cable from Tokyo to the US West Coast, for instance. So we would be getting this data in real time and analyzing it for ocean circulation, ocean temperature changes, and so on, and putting that into ocean numerical models along with all the other data. Just for reference, water basically flows from high pressure to low pressure. Therefore, if you measure pressure gradient, pressure at 2 points, you can infer ocean circulation to a large degree. And then this is something similar for the tsunami case. So for 3 cables going from Japan to the east, the 3 traces show what sensors along each cable would see as a tsunami went by. Then, sort of lastly, just for seismology, with increased seismic acceleration measurements along these cable routes, as shown in the middle plot here at the bottom, relative to no cables, there's a lot more density of sampling, and therefore we can do a better job of not just imaging the interior of the Earth, but also locating earthquakes and determining their parameters, which then feed back into better tsunami warning. So, looking more at the technical side of things, what's been done in the past using cables, all the cable systems to date have been dedicated for either early warning or scientific purposes, and these are just a few examples. The Japanese have invested large amounts of money and effort into putting in cable systems. The 2 plots on the top are from Japan. The middle one is 6 different systems or subsystems with a total of about 150 sensors distributed along 6,000 kilometers of cable. The lower right shows cable systems off the US and Canada that are purpose-built for scientific research purposes, not really early warning purposes, although they serve that purpose as well. And then the other one is a small system that we're suggesting as a candidate for smart, as a demonstration of a first step for smart systems. So there are systems out there, but they don't work with telecom. So what we want to do is combine the 2 together. And this is a cartoon of what we're envisioning, showing 2 different approaches to putting sensors into telecom repeaters. So on the top left, sensors, well, the acceleration sensors can be put inside the pressure case. They don't need to be in contact with water, but the pressure and temperature do need to be in contact with the water, and they can either sit on the end of the repeater housing or in a separate body nearby. The cutout down below shows some actual repeaters in a system. I think this is the one from Brazil to Angola, actually, a year or 2 ago. So, costs. Well, these dedicated systems are expensive. Basically all of them are on the order of $100 million for the science systems off the U.S., Canada, or Japan, and the dedicated SNET system off Japan was $300 million. So to apply that over large geographical areas is really not a possibility, and also there's high maintenance costs for those as well. So again, we're suggesting that by combining a few simple essential sensors with telecom system, we can end up with a cost-effective solution to provide ocean monitoring and tsunami and earthquake detection and early warning for reasonable cost. So this plot here shows a cost projection. Here we make an assumption that over a 10-year life cycle, cables are replaced. Now that's very, very conservative. Engineering life is 25 years for these systems, but in some cases they are replaced every 10 years, basically for financial reasons. But if we make those assumptions and we say we want 2,000 repeaters instrumented with smart capability, that would end up costing, on a sustained basis, $40 million a year. And we think the ocean observing community and early warning communities in the whole world can come up with that amount of money. So just a few comments here at this point. Just to be clear, we are still in the early stages of this project, and funding is the largest challenge. This is nothing new to most of us here. And we see at the early stages, well, and in the long term, definitely governments have to put up much of the money. Here at this early stage, multilateral development banks are willing to help as well. And I'll discuss some of the early projects we're starting in the next slides. There are commercial challenges, obviously. We need to persuade the telecom industry that this is a good idea to do. All suppliers say they can do it technically, but just need the money and time. Our approach, though, is basically start with countries that want the system, need the system, sea level rise, earthquake and tsunami, and have engaged governments and access to development bank money. So just briefly, some of the systems we're considering. This is our first funded system. It's called a wet demonstration off Sicily. Funding just came in June. And basically it's just the first demonstration. It's not a complete smart repeater development, but the first steps for that. Another one under review by the French government is between New Caledonia and Vanuatu. They have earthquakes almost every day there, and a magnitude 6 or greater at least once a month. And so they're proposing a full-blown smart system there, and that would be a pilot. I wanted to interject here, almost as an aside, but interest here. You all use optical fiber networks, and there are two new technologies that are relevant for science in general and specifically for our situation. There are two new technologies for measuring fiber strain. One measures fiber strain across a whole ocean basin over the entire length of the cable using ultra-stable lasers, and this is just in the last year, this new development. So this could be applied on land as well as in the ocean. And then the other technique is called this distributed acoustic sensing, basically sonar applied to a fiber, sending a pulse down and looking at the scattered light back. You can basically measure the stretch and elongation of the fiber, and therefore earth movement. So these are two additional technologies that may play a role. A system under consideration is this one connecting Portugal to Azores, Madeira Island, and back to Portugal. In 1755, they had a large earthquake that killed maybe up to 100,000 people and basically brought the Portuguese Empire to its close. And so they understand the need for this kind of system, and they are proposing a system that combines telecom with all of these sensing modalities. Indonesia basically has more earthquakes and volcanoes and disasters than almost any other country, I think. And so they are looking to now invest significant money in a cable-based tsunami warning system, and we are talking with them to adopt these principles. There's essentially no other financial way of doing it for them, and the dedicated systems are just too expensive, and so the smart system is the way to go. In Latin America and Southern Hemisphere, we are working with the Inter-American Development Bank, exploring possibilities for funding cables along, especially the west coast of South America and Mexico, and also into the Caribbean. So there may be possibilities there, as well as possibly going to Antarctica also. That's slightly more scientific. So next, wanted to make some connection with research and education networks. RedCLARA, basically providing connectivity and communication for the research and education communities. These maps show some of the coverage. You all know this better than I do. And then two large users, both astronomy in this case. We heard from Jeff about LSST this morning. But what we're suggesting is that because research and education networks are stakeholders in submarine cables, and significant stakeholders in some cases, and have these IRUs in the feasible right of use, they may be able to help influence the adoption of smart capability. So is this an opportunity for RENs to get involved with? So by sharing the infrastructure, we can have multi-purpose use of that infrastructure. The idea is dig once and satisfy many users, two for the price of one, if you will, and include fiber sensing and point sensors as well. So at a meeting in Miami in May, we came up, this was a meeting of regulators, and we came up with some of these recommendations. The main one is to recognize that submarine cable systems are shared infrastructure, or should be shared infrastructure, and can combine telecom with ocean observing and early warning capability. So just coming to a conclusion here, from the smart cable point of view, we are definitely now making progress. We have a funded wet demonstration project. We have several pilot systems in the works, and Indonesia's in that mix of things. We are well established within the UN organizational structure, and the development banks seem to be on board and positive. We do need to encourage more corporate social responsibility to get the companies more engaged and so on. But in the end, it really does come down to funding, and so that's my job right now, is to go and try and find that. With respect to research and education networks, climate monitoring and disaster mitigation are worthy topics for this group. And RENs can play an active role and can play a larger role and consider their networks as infrastructure to be shared. And what I'm really asking is that consider using your basically influence as stakeholders in these systems to take advantage of the possibilities of smart capability and to help the initiative move forward. Thank you.
Thank you, Bruce. No, ahora tenemos preguntas. Yo tengo algunas, si no. Yeah.
Tom Fryer from Géant on the Bella program. Fascinating talk. I can think of many questions to ask. But I mean, you've mentioned the fact that, you know, the funding is obviously one of the key elements in getting into these cable systems. But I was wondering, you know, how do you go about approaching them initially? How do you get that conversation going before you're even touching on the funding? And, you know, are you specifically looking, there are particular areas in the world that are more important than others? You know, so you look at the L-Link cable, and is that a particularly relevant cable system, or are there ones that are much more relevant than others because of seismic activity and
okay, so when we started this project, we were naively optimistic that the larger companies, Google, Facebook, would be supportive. I have to say that has not been the case. And so we have refocused on what we should have done at the beginning anyway, just from an engineering point of view, focus on smaller systems, demonstration, pilot systems. So the first one in Italy is Italian research infrastructure funding. So that's one source of funding. The New Caledonia Vanuatu system, it's a different, it's not a telecom pot of money. It's going to the French government Ministry for Territorial Affairs for much of it. And then also, because Vanuatu is a developing country, it has access to Asian Development Bank, a $5 million high-level technology development fund. So that should fund that small, manageable scale pilot system. And then lastly, we're really looking to Indonesia to take a lead. They have publicly, ministers have publicly stated that they have on the order of several $100 million US for tsunami warning. And most of that would go into what they're calling cable-based tsunami warning systems. So in this case, we're working with them, hopefully, so that they will invest the development money to get a commercial off-the-shelf smart repeater that then can be used more broadly, not just in Indonesia. And it'll be basically a checkbox on an RFP. So if we can get to that point, I'll be satisfied. And then we have to really work on getting the governments on a routine basis to fund it. I think for Indonesia especially, again, they have such a large geographical area. I really don't see any other alternative for them other than to combine early warning with telecom in that scenario. So I think a combination of those projects will end up with a smart repeater that then will be able to be used in other systems more broadly.
¿Alguna pregunta? Bruce.
Good afternoon. I expect that you understand me. Two questions, please. First question, what is the relationship between the use of smart cables in the ocean with the possibility of earthquakes? And second question, in South America, down to Chile, which countries to have the greatest risks? Especially, I would like to know what happened with Ecuador, Colombia, and Peru. Thanks a lot.
Okay. So let me, the second question, those countries do have the highest risk. I mean, it's the ring of fire. So the trench system that starts in Mexico, Baja California, going all the way to southern Chile, that is all high-risk area. And then also into the Caribbean also. Colombia just had a year or two ago a significant landslide that generated a tsunami, for instance. But there are also faults, geophysical seismic faults in the Caribbean. So all that area is at risk. And then you ask about relation between the cables and earthquakes. So in the case where you want tsunami early warning and you're really sort of perturbing our general concept of smart cables, there you're going to want to have the cable more along the trench system. And so what we're suggesting is that by deploying the cable just offshore of the trench, you can capture all the necessary, or most of the necessary information you need in order to provide the tsunami early warning. So in some cases, if a primary need for a particular cable system is early warning, in addition to telecom, the government perhaps needs to contribute more funding to get the cable along the section of interest. I hope that answers the question.
¿Alguna pregunta más? Yo tengo una. Bruce, in this period that we are living, that we are facing some disbelief in science and coming these flat Earth arguments, and how can we prove that the global warming is not just a fever?
Well, that's a much bigger problem than anything to do with smart cables. But
Yeah.
I mean, it's simply, you know, we have to keep making measurements that make it irrefutable, and we are doing that. I mean, it's not just, you know, possible cable measurements in the future which will improve the situation, but we simply need to keep making the measurements we are making and incrementally improve it and present a better story to the people in power that don't believe it. There's no magic bullet there, I think so.
Okay. Thank you, Bruce. Por favor, una salva de palmas para Bruce.